Apa saja kegiatan di iRefer tahun 2023 kali ini? Scholar Research Competition. Kompetisi riset tugas akhir untuk mahasiswa setingkat sarjana dan pascasarjana yang merupakan pencarian bibit talenta riset dan inovasi yang unggul.
Beberapa kategori yang kita lakukan dalam penjurian itu adalah kita melihat bagaimana background dari para peserta itu melakukan risetnya itu seperti apa. Kita juga melihat bagaimana keterhubungan atau keterkaitan dengan riset-riset yang saat ini dilakukan oleh BRIN. Jadi supaya para talenta-talenta muda itu nanti terkoneksi dengan riset-riset yang ada di BRIN.
Research Poster Competition, RPC, dan pameran poster ilmiah. Kompetisi untuk meningkatkan kreativitas dan kapasitas peserta dalam mempublikasikan riset melalui media poster.
Poster ilmiah adalah sebuah bentuk komunikasi atau diseminasi ilmiah, di mana poster ilmiah merangkum hasil-hasil penelitian menjadi lebih ringkas, berbasis visual, dan lebih menarik tampilannya.
Poster ini dipamerkan pada Inari Expo dan publik dapat memilih poster favoritnya.
Saya adalah salah seorang juri untuk penilaian lomba poster dalam kegiatan kompetisi ilmiah ini. Tentunya poster-poster yang hadir sangat luar biasa sekali. Saya sampai bingung gitu ya, mana yang terbaik. Tentunya semuanya baik gitu ya, tetapi harus memilih yang terbaik.
3-minute research pitch. Finalis menyampaikan ide dan hasil risetnya dalam waktu 3 menit di hadapan publik, yang bertujuan untuk meningkatkan komunikasi sains pada generasi muda dan bagaimana sains dapat diterima oleh segala kalangan.
iRefer ini merupakan bagian dari talent scouting anak-anak atau talenta muda yang kemudian kita siapkan untuk menjadi talenta unggul dengan berbagai program yang ada di BRIN ke depannya.
Talk Show Inspiring Talent. Sharing session dengan peserta program Degree by Research, Research Assistant, dan iRefer, tentang bagaimana pengalaman dan peluang berkolaborasi dengan BRIN. Melalui kegiatan ini, diharapkan terdapat talenta-talenta bangsa generasi emas 2045 yang dapat mengangkat national pride di bidang riset dan inovasi.
Semoga Inari Expo ini bisa menjadi ajang bagi masyarakat untuk lebih mendekatkan diri ke iptek, riset, dan inovasi. Semoga ke depan semakin semarak terus. Terima kasih.
Kesan-kesan mengikuti iRefer, merasa bangga ya, karena bisa lolos ke tingkat nasional ini. Kemudian saya juga merasa senang karena dengan melalui iRefer ini, riset yang saya lakukan itu mendapatkan exposure lebih tinggi lagi.
Harapan saya dalam kegiatan ini yaitu semoga kegiatan ini tetap berjalan tidak hanya pada tahun ini, tetapi juga di tahun-tahun berikutnya.
Di sini kita tuh kan bertemu dengan mahasiswa lainnya, melihat penelitian-penelitian mereka gitu. Jadi kita bisa terpacu gitu untuk melakukan penelitian yang lebih lagi gitu. Serta kita juga bisa berjejaring dengan mereka.
Semoga iRefer lebih banyak diadakan lagi dan bisa memperbanyak klasternya juga, lebih spesifik ke klasternya. Dan harapannya ke depan iRefer di tahun-tahun selanjutnya akan menambah banyak kegiatan dan memperluas jaringan. Selama kegiatan ini, aku ketemu banyak orang baru dan semuanya itu adalah orang-orang yang ahli pada bidangnya.
Perasaannya setelah menang, awalnya deg-degan, gak nyangka karena teman-teman yang lain juga sangat risetnya tuh bagus-bagus banget. Terus juga ada belasan finalis, gak nyangka pokoknya.
Ini suatu pengalaman yang sungguh luar biasa. Saya belajar bahwa untuk berani mencoba dan terus berusaha hingga akhir.
Saya sangat bahagia. Sebelumnya saya merasa agak khawatir karena mungkin nggak bakal menang atau apa. Tapi setelah dapat ini saya berasa bersyukur dan saya harap kedepannya acara ini dapat berlangsung lebih meriah lagi.
Alhamdulillah ini adalah suatu kenikmatan tentunya yang patut saya syukuri. Dan tentu saya tidak hanya dari saya sendiri, karena ada beberapa dukungan dari teman-teman terdekat, dosen juga, dari orang tua, semua pihak yang telah membantu saya hingga akhirnya saya mendapatkan pemenang dari The Winner of Poster Competition Research.
Rasanya seperti throwback moment sebenarnya. Saya kebetulan adalah finalis Elkir 2018 dan dari BRIN saya mendapatkan Special Award on Biodiversity, dan ketika di titik itu saya merasa bahwa
menjadi peneliti itu seru. Bukan tentang siapa kita, bukan tentang apa yang kita temukan, tapi tentang bagaimana kita menghargai sebuah perjuangan, bagaimana kita beranjak dari satu titik yang mungkin kita bukan siapa-siapa hingga sampai saat ini kita terus berprogres dan menjadi orang yang jauh lebih baik dari sebelumnya. Tentunya dengan bantuan orang-orang, dengan bantuan periset BRIN yang sudah memberikan apresiasinya untuk saya dulu yang nggak tahu apa-apa hingga sekarang berprogres sampai di titik ini. Tentunya sangat-sangat terima kasih kepada orang-orang yang telah membantu saya sampai saat ini.
Saya mengucapkan selamat kepada seluruh 60 orang finalis ini dan terlebih yang mendapatkan berbagai apresiasi tadi. Kita berharap ke depan juga special award-nya makin banyak ya kayak begini ya. Jadi kita carikan kawan-kawan yang bisa memberikan apresiasi secara spesifik kepada para mahasiswa, talenta muda, riset inovasi masa depan Indonesia.
Fair 2023, Expo Riset Inovasi. Kami siap menjadi talenta riset dan inovasi Indonesia.
Sampai jumpa di IRI Fair 2024.
Riset adalah kekuatan untuk kita bisa menembus segala keterbatasan. Inovasi adalah visi yang kita segerakan untuk masa depan. Kita tidak bisa sendiri. Kita harus bersama untuk membuatnya menjadi nyata. Kita tumbuh di bumi Indonesia, tempat yang magis dan penuh keajaiban. Terbentang di antara dua benua dan samudra, kaya akan keanekaragaman kultur dan biodiversitas. Indonesia dan kita adalah paduan yang dibutuhkan untuk mewujudkan visi besar di masa mendatang. Layaknya sebuah orkestrasi, Badan Riset dan Inovasi Nasional atau BRIN hadir mengharmonisasikan berbagai kegiatan penelitian, pengembangan, pengkajian, dan penerapan, serta mensinergikan riset dan inovasi di Indonesia. Membentuk ekosistem yang terdiri dari 7 kedeputian, 12 organisasi riset, dan 85 pusat riset yang diantaranya organisasi riset penerbangan dan antariksa, organisasi riset tenaga nuklir, organisasi riset energi dan manufaktur, organisasi riset kebumian dan maritim, organisasi riset hayati dan lingkungan, organisasi riset elektronika dan informatika, organisasi riset ilmu pengetahuan sosial dan humaniora, organisasi riset arkeologi, bahasa dan sastra, organisasi riset kesehatan, organisasi riset nanoteknologi dan material, organisasi riset pertanian dan pangan, organisasi riset tata kelola pemerintahan, ekonomi, dan kesejahteraan masyarakat. BRIN juga mendorong riset dan inovasi menjadi ekosistem Indonesia yang maju dan berkembang dengan 2 sasaran utama. BRIN menyadari potensi luar biasa putra-putri bangsa dalam bidang ilmu pengetahuan dan teknologi. Untuk itu, berbagai kebijakan riset dan inovasi diarahkan untuk menghadirkan kompetensi SDM iptek terbaik. Menghasilkan berbagai program unggulan sebagai bentuk komitmen BRIN terhadap periset, inovator, serta masyarakat luas dari berbagai disiplin ilmu di seluruh negeri. Peningkatan kualitas ekosistem riset dan inovasi di Indonesia juga tercipta melalui kolaborasi dengan berbagai kementerian, lembaga, industri di dalam negeri, dan pemerintah daerah, di antaranya dengan dibentuknya Badan Riset dan Inovasi Daerah atau BRIDA. Selain Selain itu, kerjasama dengan berbagai lembaga riset di luar negeri juga terus didorong. Melalui partisipasi aktif sebagai anggota dalam berbagai organisasi dan forum internasional. BRIN menata alur riset sehingga lebih efektif dan efisien dengan mengintegrasikan sumber daya manusia, infrastruktur, dan anggaran dari berbagai lembaga litbang jirap. Berorientasikan prioritas riset nasional, BRIN melakukan evaluasi secara komprehensif untuk setiap percepatan yang tengah berjalan. Upaya tersebut didukung melalui pengelolaan berbagai fasilitas riset dan inovasi yang tersebar di 17 provinsi di Indonesia dan akan terus bertambah mengikuti perkembangan kemajuan iptek. BRIN terus meningkatkan kontribusi riset dan inovasi terhadap pembangunan nasional melalui pembangunan dan revitalisasi 4 kawasan sains dan teknologi atau KST. Sebuah kawasan terintegrasi berupa fasilitas laboratorium riset, laboratorium pengujian, fasilitas industri, baik startup maupun UKM pada skala kecil atau uji coba, ruang kantor tenan, coworking space, ruang pertemuan, ruang pameran, dan fasilitas pendukung lainnya. BRIN hadir untuk mewujudkan cita-cita menuju Indonesia Emas 2045. Melalui konsolidasi sumber daya iptek, menciptakan ekosistem riset, dan fondasi ekonomi berbasis riset. Menjadikan Indonesia sebagai rujukan dunia dalam pengembangan dan pemanfaatan ilmu pengetahuan dan teknologi, kebijakan, serta kemanfaatan bagi umat manusia. Alam adalah sumber inspirasi. Ilmu adalah fondasi dan mengamalkannya untuk kemajuan bangsa.
Biar banyak koleksinya. Biar kelihatan pinggangnya biar kelihatan.
Ladies and gentlemen, kindly take your seat as the session will commence shortly. And please switch your phone to silent mode. Thank you. Announcing the presence of the Chairman of the National Research and Innovation Agency, please rise from your seat. Singing the national anthem Indonesia Raya. Ladies and gentlemen, please be seated. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning. Allow me to extend my warmest greetings to our eminent speakers and guests. Chairman of National Research and Innovation Agency, Mr. Laksana Trihandoko. Member of Steering Committee, National Research and Innovation Agency, Mrs. Tri Mumpuni. Chairman of Yayasan SDM Iptek, Profesor Wardiman Joyo Negoro. The recipient of Siwabessy Memorial Lecture 2023, First Secretary of the People's Republic of China Embassy to the Republic of Indonesia, Mr. Fu Zhenxiong. Second Secretary of the People's Republic of China Embassy to the Republic of Indonesia, Mr. Ijin Yang. Direktur Fasilitasi Riset Indonesia Endowment Funds for Education Agency, Mr. Wisnu Sarjono Sunarso. Representative of the late Professor Dr. Gerrit Augustinus Siwabessy family, all distinguished guests. Welcome to the GA Siwabessy Memorial Lecture 2023, taking place today, on Tuesday, December 5th, 2023, at the Sumitro Joyo Hadikusumo Auditorium in Jakarta. I am Jane, the MC for today's event. It's truly an honor to serve as your host today. Ladies and gentlemen, as a form of appreciation for today's event, let us gather in a moment of prayer led by Mr. Arif Surahman.
Assalamualaikum warahmatullahi wabarakatuh. Bapak-bapak dan ibu-ibu yang saya hormati, doa akan dipimpin dalam agama Islam. Bagi yang beragama lain, silakan untuk menyesuaikan. Ladies and gentlemen, prayers will be led in the Islamic religion. Please adjust based on your respective religion. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Hamdan syakirin, hamdan na'imin, hamdan yuwafi ni'amahu wa yukaffi mazidah. Ya Rabbana, lakal hamdu kama yanbaghi li jalali wajhikal karim wa 'azim sultanik. Allahumma salli wa sallim ala sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Ya Allah, kami panjatkan puja dan puji syukur kepadamu.
Recording in progress.
Karena berkat nikmat-Mu, berkat sifat Rahman dan Rahim-Mu, hari ini kami semua dapat berkumpul di tempat ini. Ya Rob, ridhoilah kami, berkahilah kegiatan kami pada hari ini. Bimbinglah kami agar dapat meneruskan semangat perjuangan para pendahulu kami dalam bereksplorasi dan berinovasi demi kemajuan, kejayaan, dan kemandirian bangsa kami. Ya Rob, ampuni dan muliakanlah para pejuang riset pendahulu kami. Berikan mereka tempat yang mulia atas jasa-jasanya, dan ilhamkanlah kepada kami agar dapat meneruskan cita-cita mereka dan menghasilkan kebermanfaatan untuk bangsa ini. Ya Rob, tunjukkanlah kepada kami jalan yang lurus, dan tunjukkanlah kepada kami bahwa yang benar itu adalah benar, dan berikanlah kami kekuatan untuk menjalankannya. Serta tampakkanlah kepada kami bahwa yang batil itu adalah tetap batil, dan berikanlah kami kekuatan untuk menjauhinya. Ya Rob, hanya kepada Engkaulah kami menyembah, dan hanya kepada Engkaulah kami memohon pertolongan. Allahumma hdina siratal mustaqim, siratal ladzina an'amta alaihim ghairil maghdubi alaihim waladdallin. Rabbana taqabbal minna innaka antas samiul alim wa tub alaina innaka antat tawwabur rahim. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzaban nar. Wa sallallahu ala sayyidina Muhammadin wa ala alihi wa sahbihi ajma'in. Walhamdulillahi rabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Arif. Ladies and gentlemen, we are delighted to present a video highlighting the profile and legacy of the GA Siwabessy Memorial Lecture. Please enjoy.
GA Siwabessy Memorial Lecture merupakan penghargaan ilmu pengetahuan sebagai bentuk apresiasi bagi insan iptek atas rekam jejak dan kontribusinya bagi pengembangan ilmu pengetahuan bidang atom dan kesehatan. GA Siwabessy Memorial Lecture ditujukan untuk mengenang semangat serta dedikasi Profesor Dr. Gerrit Augustinus Siwabessy, Bapak Atom Indonesia dan peletak pondasi pembangunan kesehatan nasional. Lahir pada 19 Agustus 1914, Gerrit Siwabessy mengawali pendidikan di Mulo Ambon. Kecermelangan akademiknya mengantarkannya memperoleh beasiswa dari pemerintah Hindia Belanda untuk berkuliah di Netherlands Indische Arts School di Surabaya. Gelar dokter diperoleh setelah ia lulus ujian arts di Sekolah Tinggi Kedokteran Universitas Indonesia di Batavia. Semasa menjalani ikatan dinas sebagai dokter di Pusat Pengeboran Minyak Belanda di Cepu, ia diminta untuk membantu bagian radiologi Rumah Sakit Simpang Surabaya. Lalu dengan beasiswa British Council, Siwabessy melanjutkan pendidikan di University of London, Inggris. Bidang radiologi, radioterapi, dan pengetahuan dasar atom yang dipelajari selama di Inggris kelak membuka riset bidang atom di Indonesia. Siwabessy juga mempelajari sistem jaminan kesehatan Inggris yang lalu dikembangkan menjadi ASKES, sebagai cikal bakal jaminan kesehatan nasional. Uji coba bom nuklir oleh Amerika Serikat di Pasifik pada tahun 1952, mendorong berdirinya Lembaga Tenaga Atom yang menjadi cikal bakal berdirinya Badan Tenaga Atom Nasional pada tahun 1964. Siwabessy ditunjuk sebagai Direktur Pertama Batan dan diangkat sebagai Menteri Tenaga Atom. Di bawah kepemimpinannya, Indonesia berhasil membangun reaktor atom pertama 3 Mark II di Bandung pada tahun 1965, diikuti pembangunan fasilitas riset atom lainnya, seperti Laboratorium Isotop dan Kimia Nuklir di Pasar Jumat, Jakarta dan Pusat Penelitian Tenaga Atom Gamma, di Yogyakarta. Saat menjadi Menteri Kesehatan, Siwabessy berhasil membawa Indonesia bebas penyakit polio pada tahun 1974. Selain itu juga mewariskan konsep fasilitas layanan kesehatan puskesmas yang manfaatnya terus dirasakan sampai hari ini. Jasa-jasa Siwabessy mengantarkan putra Saparua ini mendapatkan bintang Mahaputra 3 utama di bidang tenaga atom serta bintang Mahaputra 2 Adhi Pradana di bidang kesehatan. Namanya juga diabadikan sebagai nama reaktor riset terbesar se-Asia Tenggara dengan kapasitas 30 MW yang berlokasi di Serpong, Banten. Dedikasi hingga akhir hayatnya memberikan sumbangsih besar bagi perkembangan riset atom dan kesehatan di Indonesia sampai hari ini. Pada tahun 2022, BRIN memberikan apresiasi kepada Profesor Dr. Muhayatun MT, sebagai pemberi kuliah ilmiah GA Siwabessy Lecture 2022. GA Siwabessy Memorial Lecture menjadi lebih dari sekadar sebuah penghargaan. Ia mewakili warisan ilmu pengetahuan dan semangat dedikasi. Semangat ini, semoga menjadi terang penerus perjalanan ilmu pengetahuan Indonesia yang terus berkembang.
Let's give a round of applause. Now, let's delve into the profiles of the recipient of GA Siwabessy Memorial Lecture 2023 through a video presentation.
In the world of nuclear engineering, one name stands out, a name synonymous with excellence, innovation, and a lifelong commitment to advancing nuclear technologies. Today, we delve into the illustrious career of Dr. Yuliang Sun. Dr. Sun, a distinguished scholar with a foundation in nuclear and mechanical engineering, earned his degree from the prestigious Engineering Physics Department of Tsing-Hua University in Beijing, China, in 1984. Taking his pursuit of knowledge further, in 1992, he obtained his Dr. Ing. degree in mechanical engineering from the Technical University of Aachen, Federal Republic of Germany, a testament to his global perspective. Today, he serves as the Deputy Chief Engineer of the Institute of Nuclear and New Energy Technology at Tsing-Hua University, contributing significantly to the education, research, and development of nuclear technologies. Dr. Sun has played a pivotal role in the research and development of high-temperature gas-cooled reactor technologies in China, leaving an indelible mark on the country's nuclear landscape. His main interests lie in the realms of advanced nuclear reactor technologies and nuclear safety. A former deputy director of the Institute of Nuclear and New Energy Technology, he has also held senior managerial positions in the nuclear industries. Internationally, Dr. Sun's influence extends to prestigious roles such as serving as a member of the International Atomic Energy Agency's Technical Working Group of Gas-Cooled Reactors, member of the expert group of the Generation IV International Forum, and director of the Nuclear Power Division of the IAEA. Currently, as a professor of nuclear engineering at Tsing-Hua University, a member of the expert committee of the China Nuclear Energy Association, and a member of national expert committees for ecological and environmental protection and nuclear safety, Dr. Ing. Yuliang Sun continues to shape the future of nuclear technology with unwavering dedication.
Meet Dr. Jun Sun, a distinguished expert in engineering thermophysics and power engineering from the School of Aerospace at Tsing-Hua University in Beijing, China. In 2009, he achieved his PhD and embarked on a remarkable journey at the Institute of Nuclear and New Energy Technology, Tsing-Hua University. Today, he stands as the division head of reactor physics, thermal hydraulics, and systems simulation, leading groundbreaking research in high-temperature gas-cooled reactor technologies in China. Dr. Jun Sun is deeply passionate about education, dedicating his expertise to the fields of reactor thermal hydraulics, nuclear reactor simulators, and advanced nuclear system designs. As an associate professor of nuclear engineering at Tsing-Hua University, he not only imparts knowledge but also serves as a guiding force for aspiring engineers. Beyond his academic role, Dr. Jun Sun is an active member of the Nuclear Reactor Thermal Hydraulics Branch Council, Chinese Nuclear Society, and proudly represents China in the Education and Training Working Group at the Generation IV International Forum. With his relentless dedication to research and development, Dr. Jun Sun continues to shape the future of nuclear technology in China, leaving an indelible mark on the global stage.
Let's show our appreciation with a round of applause. Advancing to our next agenda, as we delve into the lecture session, I invite you to join me in giving a warm welcome to Professor Dr. Ing Sun Yuliang.
Mr. Chairman, senior officials from the Chinese Embassy, ladies and gentlemen, good morning. Well, first of all, I would like to thank Mr. Chairman, for the nice invitation to give a lecture or presentation on this very important event. I do regard it as a great honor. And also my thanks go to the working team for the presentation of my biography. That's the nicest I've ever had of my own biography, much better than I prepared by myself. Thank you. We are supposed to present or to address about the development of high temperature gas cooled reactor technology in China. And my co-author is Dr. Sun Jun. We represent first the Institute of Nuclear and New Energy Technology of Tsing-Hua University. And secondly, we also represent the China-Indonesia Joint Laboratory on high temperature gas cooled reactor. Okay, firstly, let me have one slide about my institution, my institute. The institute was founded in 1960, and since then it has been one of the major nuclear education, research and development institution. With engineering capacity under Tsing-Hua University and the Ministry of Education in China. It has about 35 faculty or staff members and over 350 postgraduate students. It is equipped with a number of research or test reactors, which we have designed and built by ourselves, and a number of laboratories. The major research and development fields include nuclear reactor technology, nuclear fuel reprocessing, nuclear waste treatment, radiation application, new energies, and energy policy studies. Okay, we have time. So the main topics of our talk today include the energy supply and the nuclear power situation in China, to give you an understanding of under what background or under what environment we are working in the high temperature gas cooled reactor. And then we want to introduce about the HTR technology as a general option of nuclear power technology. And the next three topics are the gas cooled reactor development work we have been conducting through the past decades, the test reactor, the industrial demonstration plant, and the future planned nuclear high temperature gas cooled reactor projects. And then I will come to the international cooperation, which had been playing a very important role in our gas cooled reactor development. And there I would also get back to the China-Indonesia high temperature gas cooled reactor joint laboratory. Last but not least, the summary. So talking about the energy supply and the nuclear power development in China. First, as you probably all know, China experienced very fast economic growth in the past 2 decades. The GDP value in the year 2000 was $1.2 trillion US dollars, and that value in last year was about 18 trillion US dollars. It is a factor of about 50 times in a time period of 22 years, making China the world's second largest economy since 2020. But you also know that China has a large population, and the per capita of GDP is relatively low, let's say. That value of 2022 was only about 12,800 US dollar. It is still only slightly higher than the world's average of 12,459 US dollars. Slightly higher, but only for the first time last year. So basically, or roughly we can say Chinese economy in terms of per capita value is at the world average right now. Now the third point, for further development, the national medium-term goal for China is to become a moderately developed country by the year 2035, something like 16 years from now, meaning specifically that the economic level or income level will be doubled by then, comparing from 2020. Okay, thank you very much. With the GDP value reaching about or over 30 trillion US dollars. So this fast economic growth has to be or needs to be powered by energy, in particular electricity. And you can see from these two figures, this fact. The first picture is the energy consumption of total energy. The second figure is power generation or consumption of electricity, of electrical power. You can see that the obvious fact is the fast growth in the past 2 decades, in the past 20 years or so. Now, securing such large amount of energy supply, meaning a lot of, or faces a lot of challenges, many challenges. First is to meet the energy demand. You have to have a lot of energy resources to supply that amount of energy. And then energy security, to secure the energy supply. Since the years, China's energy supply, of which about 20% has to be imported. So we want to be sure that this energy supply is always being secured. And thirdly, we have a lot of, let's say, pressure or challenges in terms of environmental protection or carbon dioxide emission control. And this requires a great restructuring or structural optimization of the energy supply spectrum. China still depends a lot, or used to heavily depend on coal for its energy supply, for power generation. And this fact has to be changed or optimized from the viewpoint of carbon dioxide emission control or zero emission target. Last but not least, one of the national policies is to create and to maintain high-tech industries, and this is also true for the energy sector. And the nuclear power is a good example to have a strong and to have a strong high-tech technology, because nuclear power plants covers a wide spectrum, a wide range of industrial products. Where should I point this controller? Okay. Now, talking about nuclear power application. Now, the first fact is, in the past 2 decades, nuclear power generation also witnessed the fastest growths. And you see this fact on this picture. For the last, this picture goes until the year 2020, I think. You can obviously see the fast growth of nuclear power generation. Although the absolute addition of nuclear generating capacity is growing very fast, and also the power generation, the generated power by nuclear is also growing very fast. But because China has such a large total amount of consumption of energy and electricity, nuclear power now, the share or the percentage of nuclear power is still not high. It's right now not as high as 5%. It's under 5% nuclear power shares percentage. Now, some concrete numbers about nuclear power plants. By September this year, 55 nuclear units are under operation, and they have a total installed capacity of 57 gigawatt, contributing to about to 4.87% of the total generated power this year from January to September. And also by that time point of September this year, 20 nuclear units are under construction with a total capacity of about 28 gigawatt. So certainly China has the largest number of nuclear power plants under construction. And here I think I should congratulate the nuclear industries in China. They have been very successful in terms of good performance of building and operating nuclear power plants. And also we have today representatives from the nuclear industries. Congratulations to them. Now for the future, it is expected that by 2035, 70 years from now, nuclear power may take up to about 10% of the total power generation in China, with installed nuclear generating capacity well beyond 100 gigawatt. So that is almost for sure if nothing disastrous happen in the meantime. For example, severe nuclear accident. If nothing happens like that, nuclear generating capacity will go beyond 100 gigawatt. So that would make China the largest nuclear power generation country. To meet the nuclear power development goal, China is, in addition to light water reactors, also developing other advanced reactor types, nuclear power plant technologies. For example, high temperature gas-cooled reactor, which I will get back very soon, fast breeder reactor, molten salt reactor, so on. So now let me get to the high temperature gas-cooled reactor technology. We are all pretty much familiar with light water reactor nuclear power plants, which is the mainstream of the world's nuclear power plants and also the mainstream nuclear power plants in China. And with this table, we can very simply see the differences between these two technologies, light water reactor and high temperature gas-cooled reactor. These are two very different technologies. What they have in common is they all use uranium dioxide as the original nuclear fuel material. But with the light water reactor, the uranium is cladded by metallic material, metallic cladding. With gas-cooled reactor, the uranium dioxide is cladded by ceramic materials, pyrocarbons, silicon carbide. These are ceramic materials. Coolant, there you have light water, and here we have helium. Neutron moderator, there is also the light water, here is graphite. Core structure material within the reactor, there is metal, and here is graphite. So, well, I think we can say these are two very much different nuclear power reactor technology. So the core of the high temperature gas-cooled reactor technology sits in the fuel. And that technology relies its safety pretty much on these forms of fuel, what we call coated particle fuel. Or more specific, right now the technology is trisol coated particle. And there we have, as the red kernel of uranium dioxide, diameter is only about 0.5 millimeter. And this uranium kernel is coated by several layers. Mostly we say three layers, and that is why we call it trisol coated particles. 3 layers of ceramic materials, which are explained here on this slide. The kernel I mentioned it is now uranium dioxide, but it could also be other forms of nuclear fuel with thorium or with uranium-plutonium mix. 3 layers we usually talk about is the pyrrocarbon layer, the 2 yellow layers of pyrrocarbon, inner pyrrocarbon layer, outer pyrrocarbon, and the silicon carbide layer in between. And these layers are strong enough to retain all the fission products, all the radioactive materials within the coated particle. From that basic coated particle technology fuel, it evolves into 2 forms of nuclear fuel elements. One form is the spherical form, which you see on the upper left corner. And the other form is the so-called prismatic fuel element, which is lower right corner. And these are 2 options of nuclear fuel elements, fuel technological options. And these 2 options are, I think I have the next slide. These fuels is full ceramic, it's high temperature resistant, and in normal operation right now, the temperature specification, let's say, is 1200 degrees centigrade, and in accidental situations, it can stand up to over 1600 degrees centigrade. Within this temperature domain, these coated particles demonstrate very good performances in terms of fission products retention. But it's a different fuel technology, so you need a different fuel manufacturing technology in comparison to the light water reactor fuel technology. So these 2 reactor fuel element technologies are pursued both worldwide. The spherical fuel element on the right and the prismatic fuel element. The spherical option is pursued more in Germany and currently in China. Prismatic option more in the United States and in Japan. Now, the next most important material, helium, working as coolant through the reactor. It's a good gas coolant for reactor application because it is chemically inert, it is not corrosive, it is a single phase gas, stable with varying temperatures, and in terms of neutronics, it is transparent. It does not have a role to play in the neutronic balances, does not absorb neutron much, and it does not moderate neutrons much. Challenges with helium include it's easy to leak, as we all know, and it generates a more fractional environment where we have helium and we have rotational equipment or moving equipment. We have to solve this problem with high friction factors, high friction efficiency. And it is not as effective or efficient as light water in terms of heat transfer. So it requires more efficient heat exchanging technologies. Okay. Now the next important material is graphite. Graphite is also a relatively widely used nuclear material as neutron moderator and as core structures. It has very low neutron capture sections, does not absorb neutron very much, but it has a good neutron moderation capacity, making these neutrons flying much slower. But not as good as light water. It has a high thermal conductivity, it has a significant thermal inertia, large volume, and it is high temperature resistant. The challenges with graphite is need to have a special material preparation and manufacturing technique, know-how, and graphite degrades with neutron irradiation. That affects the lifetime within the reactor working conditions. which you have to take into consideration when you design and operate the reactor. So here are some pictures of graphite material, graphite blocks, with real reactors or with experiments. The first picture is a South African with a South African project. The upper right picture is from Fort St. nuclear power plant of the United States. And then the lower two pictures at the bottom are from the Chinese projects. Left is from the test reactor, the right is from the current ongoing demonstration power plant. See the graphite blocks. So from these basic technological choices, we can make some conclusions about the generic technological features of high temperature gas cooled reactors. Almost all of these features come from the selection of materials, right? First, a uranium-helium graphite system can resist high temperature so that you can realize high temperatures from reactor operation. Typical temperature range is from 700 to 1000 degrees centigrade. And because you have these high temperatures, if you use it for power generation, the power conversion efficiency will be much higher, which will be higher. And these high temperatures also allow for process heat applications at various temperatures. Now, one important neutronic aspect is such a system has a strong negative neutronics feedback effect, which means if you have something there abnormal or accidental inside the reactor core, the reactor tends to shut it down by itself, which basically means you can exclude the possibility of nuclear accident type of Chernobyl. And then it is a chemically inert system, but it is less compact. It has a lower core power density. That means if you want to have a same level of nuclear power output, thermal power output, you have to have a larger size of the reactor when comparing to a light water reactor or fast breeder reactors even more larger. Basically because the neutrons travel in graphite much longer than in water or in fast reactor coolant. And also because certainly helium does not have a very, very strong heat transfer. Helium and graphite system does not have that strong heat conduction, heat transfer efficiency, let's say. But these large thermal inertia of that system would provide the opportunity of slow transients. When you have something not normal, it goes slowly, not that fast, which gives you time of enough time to respond. Okay. The idea of high temperature gas cooled reactor was not new. It went back to the years of 1940s, even early 1940s. A professor at University of Wisconsin, a professor of chemistry, Professor Farrington Daniels, proposed the picture here. You see, even in 1940s, the high temperature gas cooled reactor plant. It was a challenging idea, challenging proposal. Helium gets into the reactor at 100 degrees centigrade and out of the reactor at 2000 degrees. So, but it's a scientific proposal. That is what scientists can do. But with this, I would like to say high temperature gas cooled reactor has been a concept, a technological option in the world through the years, worldwide. Now, worldwide, a number of high temperature gas cooled reactors either testing reactor or experimental reactor or nuclear power plants have been built in Britain, in Germany, in the United States, even from testing reactor to industrial power plants at the power level of about 300 megawatts were built and operated. And unfortunately, these high temperature reactor facilities or power plants came to a close. Almost every facility came to a close before 1990. And after that, Asia take that technology and starts to put resources into the development of this technology. China builds a test reactor, and Japan also built a test reactor. Those two red reactors, let's say. Japan's reactor calls HTTR, and Chinese one is called HTR-10. I will not go into the design specifications more specifically, because I understand that you don't wish the presentation to be too long, right? I think we can say that, or it is a fact, gas-cooled reactor development has not been successful as the light water reactor technology, right? They were built in the 1960s, 1970s, operated until late 1980s, and then they came to an end in Germany and in the United States, in the two primary countries who have spent a lot of resources in the development of this technology. There are complicated reasons for this historical fact, but one important fact is the 3 Mile Island accident at the end of 90s in 1979, at the end of 1970s in 1979. And after that accident in early 1980s, gas-cooled reactor people, both in Germany and in the United States, they thought about it carefully, how to make the nuclear power plants safer. And they came to the modular concept, modular TGR concept, to avoid the accident type of 3 Mile Island, to avoid that a nuclear power reactor can have cold melt. Reactivity would go out of the fuel element, even go out of the reactor vessel, even out of the nuclear power plant. So with this as the main consideration, or as the goal of the consideration, they came to the modular HTGR concept or designs. On the left side, you see the proposal of the General Atomic Company in 1980s. On the right side, the Siemens proposal of modular concept, also early 1980s. I think the proposal was firstly made in 1981 or 82, something like that. Now, what are the key technical features of the modular proposal, modular gas-cooled reactor design proposal? The first most important thing is the reactor, or the reactor would have a lower power rating, lower power generating capacity. It will also have a low power density. The reactor will have a slim configuration of the reactor core itself. These are basically considerations, selection, design choices to allow the reactor heat after it is shut down to go out of the reactor by itself. So to eliminate the possibility of 3 Mile Island accident type. And then I call it descended and separated arrangement of steam generator from the reactor. The reactor and the steam generator are arranged separated, not one over the other or under or below the other, underneath the other. They are separated basically to separate the helium environment and the water steam environment. As you know, the steam generator, there you have water and steam. In the reactor, you have helium. In such arrangement, you can better separate the two working environment. Earlier, large gas-cooled reactor designs came to the use of concrete vessels, big reactors. Steel vessels cannot house the reactor. And now because the reactors become small, becomes modular, the use of steel vessels, the idea of use of steel vessels came back. The reactors, the steam generators are all housed in steel pressure vessels. Unlike with the THTR reactor in Germany, the nuclear power plant of a pebble bed type, the control rods, control elements, neutron control elements will not go into the pebble bed itself, which will cause damages to the fuel. They only serve to control the reactor in the outside of the reactor core in the so-called reflectors. Now for pebble bed option, pebble fuels, because the reactor becomes much taller, slim, the fuel will go through the reactor core not once, multiple times. So these are, I didn't do anything. These are basically the important technical features of this going modular idea. The outcome, the end result is, or the idea is, if you want to have a large nuclear power plant, if you need larger generating capacity, you build several or more such reactor modules to meet your energy demand, to meet your power generating demand. How much time? Okay. Now, the striking features, most important features of going modular is to have a better safety, we can explain these better safety features in terms of neutronic aspect, heat removal aspect, reactivity, retention capacity, the three aspects. And with modular reactors, in all of these aspects, I should say it has much more advanced features or unique features. You will avoid Chernobyl type power plant accident. You will be able to avoid 3 Mile Island type nuclear accidents. And in the end, the design goal is there will be no off-site nuclear emergency required, meaning there will be no significant radiological impact outside the nuclear power plant boundary. And this is, by the way, this is also the requirement in the so-called Generation 4 international development. I've talked about the worldwide nuclear gas-cooled reactor construction operations. There are several who were already realized. And in the early 1980s, the development line went into the modular ideas. Not old, the previous gas-cooled reactor plants were later on shut down, and projects were unfortunately cancelled. So the whole world follows the idea of modular reactor technology. And specifically, as I mentioned, Japan built a test reactor of 30 megawatt power with 30 megawatt capacity, and China built a test reactor with 10 megawatt capacity. All these two test reactors follow the ideas of modular reactor design. The purpose is also to demonstrate the modular reactor concept. And after these two test reactor, I think from our side, we are trying to go to the next step for industrial demonstration and commercialization. But also we are also actively participating in the so-called VHTR research and development, which is more a focus in the Generation 4 international forum. Now from the world, let's come to China, which you are more interested in. Now the roadmap, I think we can say, there are 3 or 4 major steps which we want to go through until the commercialization of this technology is realized. The first step is research and development, R&D. The second step is to build a test reactor. The third step is to go industrial demonstration with a prototype power plant, let's say. And the last step is to go to commercial. In the year 1970s, we conducted a lot of research and development work, R&D work. We did a lot of testing on the vessel, on graphite, on fuel handling, on many things. The development goal at that time was to build a 100 megawatt thorium thermal breeder. And it was a very demanding, challenging goal. Although we didn't build that in the end, but we did a lot of experiments. And in the 1980s, as I mentioned, when the whole world went into modular, we also followed the modular concept. We did basic researches, modeling, software development, experimental work on the modular reactor concepts. We developed codes, the computer code system for design analysis and accident analysis. We also performed application studies for heavy oil recovery, for petrochemical industries, even together with the German industries. There were a lot of bilateral cooperations between Germany and China. Yeah. And in the 1980s, we proposed to go to the second step, to build a test reactor. The objectives and purposes of building a test reactor is to acquire the experiences of design, construction, and operation, and to carry out testing of the fuel, to verify the claimed safety features of modular gas-cooled reactor, and to demonstrate some application features like cogeneration, combined cycle, and so on. So these were the objectives set at the beginning when we proposed to build the test reactor. And the proposal, the test reactor idea was included in 1986 into the Chinese National High Technology Program, 1986. And in 1992, the government officially approved the construction of that test reactor. And after that, we started to pour the concrete, to manufacture equipment, to construct and to commission and so on. Until the year 2000, that test reactor went critical. And 3 years later, in 2003, it went into full power operation. These are pictures taken during the construction of the test reactor and when it went firstly critical in the year 2000. So that is the cartoon, the basic principle of how the test reactor works. You see on the left side the reactor, on the right side the steam generator, the fuel elements, the core, the control room, the right lines moving are the flow of helium coolant. So that is the working principle of that test reactor. And on the left are some design specifications, design parameters of the test reactor. Okay. Fuel handling, charging and discharging these spheres is a specific technological feature of this type. And this is how the fuel handling of these spheres works. You put new fuels into the reactor, discharge the spent fuels. You have to discriminate or separate the spent fuel with other types of spheres like graphite spheres from the reactor. This is a unique system and also a challenging system. Need a lot of handling. The test reactor could operate in several modes. It can generate electricity only. It can also operate in a cogeneration mode, electricity and heat supply, and it can also work by generating only heat without electricity generation. It is a small test reactor, so generating electricity sometimes is not that worthy, in particular from the grid. So many times or very often it is operated in a mode not generating electricity. These are operational histories of the test reactor after first criticality and in the last couple of years. It's typical with experimental or test reactors that they are not operated full-time every day or every month. Important with the operation of this test reactor is to demonstrate the safety features of the modular reactor concept, which are the initial objectives of developing modular. So with this test reactor, a number of safety demonstration tests were performed. Some even very demanding or challenging accidental situations, like you stop the cooling, you withdraw the control rods even without scrambling it. So these kind of safety demonstration tests were performed with this test reactor. And at one time, IAEA even organized a team of international experts coming to us and witness the progress, the procedure, the progress of such safety demonstration tests. This picture shows that event. I'm pretty sure we have Indonesian colleagues in that team, but I'm not sure within this picture. Okay. To summarize the experience or lessons we have learned from the test reactor, I think we can say we were very successful in the fuel technology development. The fuel in the test reactor was manufactured by our institute, a group of fuel people, and we have collected good experiences with the plant technology, with the systems and the equipment. We have, as I just mentioned, we have performed meaningful, very useful safety demonstration tests, telling the world, telling the general public, telling the government officials that this reactor type, in its modular design, does possess these safety features. Of course, through that test reactor, we have also been successful in terms of capacity building, people doing research and development, engineering, manufacturing of the industries, commissioning, operation, and maintenance. So I think that was a very successful experience. The test reactor helped us a lot in acquiring this technology, acquiring the necessary people, necessary experience, so that we can go on to the next step. The next step of building an industrial demonstration plant. The idea of the initiative of doing industrial demonstration started in year 2004. And in the year 2006, the gas-cooled reactor demonstration project again became in 2006 one of the national key projects of China's 2020 National Science and Technology Development Program. So that means the central government is supporting that project to a certain extent, provides some budget, but the major part of the budget still came from industry, from other resources. But the central government provides an administrative and some budget support of this project. It is within the National High-Tech Program, and this is already important enough for us to implement that project, I should say. So this is the idea I have just mentioned. The central government play an important role in leading this project. And at the working level, we have my institute, ANET, doing the plant general design, engineering of systems and components in the nuclear, within the nuclear building, the reactor, nuclear-related systems and components. We have the industry, the vendor industry, doing the general engineering and procurement, construction, civil engineering, and so on. And then at the right side most, the user, the operator industry, the Huaneng Group, one of the major power generation companies, is let's say the buyer, the operator of that power plant, demonstration plant. This is basically the structure of the project. Now these are design specifications of that demonstration plant, which we call HTRPM, High Temperature Reactor Pebble Bed Module. That is what HTRPM standing for. Within this demonstration plant, we have 2 reactors, 2 steam generators being connected to 1 steam turbine. And that is basically the idea of modular power plant. When I need a larger capacity of the plant, I build more reactor modules. And in this specific case, we have 2 reactor modules. So I don't want to go into the detail of the design specifications. That was the idea of the demonstration plant. The construction site, if I think some of you visited that site, maybe. It is in the Shandong, it's on the coastal side in the Shandong Peninsula. 1 hour flight from Beijing. This is a computer 3D representation of the plant design. And on the left side is the nuclear building. The right side is the turbine building, turbine generator building. As I just mentioned, our institute, although it is under a university, is responsible for the major part, for the greater part of what you see here in the reactor building. The reactor, the steam generator, the control rods, fuel handling, fuel storage, and so on and so on. So that's in our capacity, engineering capacity of my institute. From the test reactor to industrial demonstration, that's a big step. You can imagine. The test reactor is 10 megawatt. The demonstration reactor is 250 megawatt. So that's 25 times larger in terms of capacity. So we need to do a lot of verification to demonstrate that the engineering, the design will work, would be correct, would work in a real operational condition. So we built an engineering lab, and in the lab we built a 10 megawatt helium loop. With this helium loop electrically heated, we can perform experiments, testing of various designs, of control rods, of steam generator, of helium blower, of all of these things, fuel handling and so on, with the real temperature, real pressure, the real reactor operational conditions. So we do a lot of verification. Fuel, also, we established a new production line of the fuel and produces sample fuels for the demonstration plant. And these are experimental rigs, test facilities for the systems that I've just mentioned. Equipment manufacturing. Most of the equipment components are manufactured in China, with the exception of the graphite blocks, which comes from Japan's Toyo Tensor company. Fuel production is or has been a successful story. Our institute developed the whole process, the production line, production technology, and then we transfer this production technology to the industry. And now, later on, the fuel elements are being produced by industries, not by our institute at a university. These are the radiation results of our fuel performing excellent. This is the commercial fuel fabrication plant I just mentioned of the nuclear industry in Baotou City. Dr. Saif, I think he went there, and some of our colleagues of that time, Bataan, visited that fuel factory, fuel company. Helium circulator, steam generator. I don't have much time, so I need to hurry up a little bit. Control rods, fuel handling, spent fuel storage. And here is a summary of milestones of that demonstration plant. I just mentioned in 2004, we started that initiative. 2006, design was finalized. Well, numbers of important milestone events. What is the current situation? Since 2020, we came to the commissioning stage of that demonstration plant, from hot testing, from cold testing, hot testing, fuel loading, turbine testing. So all of these commissioning activities. From last year until now, the effort is to operate that demonstration plant at full power, step by step, under the supervision of National Nuclear Safety Regulation. You see, last December, the December of 2020, the two reactor modules reached 200 megawatt thermal. The full power rating is 250. So that is a process that we are now undergoing. This year, commissioning and preparation planning for full power operation, as I just mentioned. Now that was basically a story, a review of the demonstration step, right? I mentioned from research to testing to demonstration. And now I come to the next step, commercialization. And before I start the commercialization step, I think we, as the developer of that technology, have to position that gas-cooled reactor technology in an appropriate way, in a reasonable way. We think, as I mentioned, the mainstream of nuclear power in China is light water reactor technology. So we think a gas-cooled reactor is a supplement to light water reactor. And it is specifically suitable to replace coal-fired power plants to reduce the share of coal, optimizing the energy structure. And it is suitable for cogeneration of steam and electricity for process heat application. And based on these considerations, we came to a design of a 600 megawatt plant, which we call HTRPM 600. That would use the proven technologies we got from this demonstration project and will be, promoted in suitable marketplaces. And right now we have several projects under preparation of this 600 megawatt plant design. So that's again a computational, a computer 3D presentation of that plant. It's just one option. Now, as a research and development institution of the university, we are not doing only industrial effort, but also spend a lot of effort on research and development for more technological advances, like using supercritical steam generator to further increase the power generation efficiency, our gas turbine technology, hydrogen production technology. So our institute, what I mentioned has been mainly the industrial line. Now the research and development line, we are also following with these tasks, for example. So I came to the point that the central government supports us a lot, and this is a proof. You see 3 pictures, the state leaders, the president, visiting during exhibitions, visiting our exhibition booth, let's say, and talking with our people. And I think he himself, the president, he is also a graduate from Tsing-Hua University. And I think he knows this technology, maybe not, okay, I think he knows the technology and knows well the progress of this technology. Yeah, as I promised, I have a few slides about international cooperation. Through the years, we have always been very positive and active toward international cooperation in many forms, in various forms. And this helps us a lot in many aspects. For example, with IAEA activities, doing coordinated research, benchmarking, and so on. Generation 4 forums. I mentioned we had a lot of cooperation with Germany, with the German institutions, and even individuals. We have other bilateral collaborations such as Japan, USA, EU countries or institutions, etc., etc. And I want to get back specifically to the idea of to the joint laboratory on gas-cooled reactor between China and Indonesia, which started how many years? 6, 7 years ago. Let me have a quick review. This China-Indonesia joint lab on gas-cooled reactor, on high-temperature gas-cooled reactor, was an agreement or a decision made between the 2 governments at the minister level between China and Indonesia. In the year 2016, in August, they signed an agreement between the ministers. I would like to read one paragraph from the original agreement. The two parties agreed to establish China-Indonesia Joint Laboratory on HTGR, hereafter referred to as the HTR Joint Laboratory, as a platform for conducting high-level joint research, enhancing exchange and training of researchers, and encouraging technology transfer so as to strengthen the scientific and technological capacity building in Indonesia and build up a cooperative relationship in the development of HTGR in the long-term and steady way between the two countries. Okay, I think that has been a most important instruction to us when we do the implementation of this joint laboratory. In the year 2017, state leaders from two countries unveiled the plate of this joint laboratory. If I'm not too wrong, it was also in this building. Probably, yeah. Okay. Now, what do we do within this joint laboratory? We do joint studies on reactor designs. We do joint studies on safety issues and licensing approach. We have compared the licensing approaches, differences, or things in common in our licensing approaches in the two countries. We have done joint studies on localization and project models. We have been studying the Indonesian industrial capacities to participate in a nuclear high-temperature reactor project. We have done joint development of simulation platforms. So you see trainings and on software systems and modeling. We have done joint reports and publication. And you see our people at the working level. It's really a very good cooperative environment, really like colleagues. Yeah, the joint lab is now being upgraded to deepen, widen, and strengthen the cooperation, I should say. Less than a month ago, your respected Mr. Chairman visited our institute. This is the proof of the visit, you see. And he visited our reactor and experimental facilities. And from our side, I have the feeling we have representatives from the Chinese government here, the Chinese embassy. China's government attaches great importance to this cooperation initiative. As a summary, I think I listed a few points. First, the modular gas-cooled reactor technology have advanced and unique safety and high temperature features. And this makes it capable of fitting into certain markets of power generation, cogeneration, process heat application, hydrogen generation, and so on. Beautiful things, but we need to push it for realization. After more than 40 years of experiences in HTGR research, development, testing, demonstration, we in China are now in the stage of commercialization of this technology. As I mentioned, we have now several projects under preparation of going commercialization. Now, to reflect, what are the factors which are essential, which are important for our development in China of the gas-cooled reactor technology? It has been a long history since the 1970s. So we have a lot to reflect, to think about. It's really long. First important, I personally think, is the demand, the energy demand. If there is no demand, you only have passion. That's not enough. I think energy demand is mostly important, firstly important, and then for nuclear technology development, national policy and governmental support is important, is essential. Third, persistent, continuous commitment of a development team, because it's a sophisticated task of development. So the team has to be really persistent. And we have to follow the necessary path, the way, in order to avoid big mistakes, failures. And cooperation and involvement from industries or from industrial stakeholders are critical, very important. If you don't have cooperation from the industry, then realizing a real project, industrial project, is impossible. So the industry has to have its interest and its benefit, let's say. Last but not least, international cooperation, that we support each other, help each other internationally. I think that is the last slide. I thank you all for your kind attention. Thank you very much.
Thank you, Professor. Kindly remain on stage for a moment. We extend our thanks to Professor Sun Yu Yang for imparting his valuable expertise with us. Once again, let's give a round of applause. Next, I would like to invite Dr. Sun Jun to join us on stage. Please remain on the stage for a moment. I would like to invite Dr. Sun Jun to join us on stage. I would like to invite Mr. Laksana Trihandoko and Mr. Wisnu Sarjono Sunarso to present token of appreciation. Thank you, Professor Sun Yu Yang and Dr. Sun Jun, for your exceptional contribution. Congratulations on your achievement. Let's capture this moment in a photo session. I warmly invite our VIP guests to join us on stage for a group photo. Mrs. Tri Mumpuni, Profesor Wardiman Joyo Negoro, Mr. Edi Giri Rahman Putra, Mr. Fu Junxiong, Mr. Isin Yang, high-ranking officials, Chairman of Research Organization at the National Research and Innovation Agency, and I invite representative of the late Professor Dr. Gerrit Augustinus Siwabessy family. Smile, 3, 2, 1. One more. 3, 2, 1. Thank you. Thank you all for the wonderful photo session. Kindly take your seat. Mr. Laksana Trihandoko, please remain on stage. Ladies and gentlemen, welcome remark by the Chairman of National Research and Innovation Agency, Mr. Laksana Tri Handoko.
Terima kasih, Bapak Ibu sekalian. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sehat dan sejahtera untuk kita semua. Salam, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Very good morning, everyone. Ladies and gentlemen, yang saya hormati Dewan Pengarah BRIN, ada Ibu Puni di sini, kemudian juga dari Pak Wisnu, dari LPDP, para pejabat dan pimpinan di lingkungan BRIN, ya, Kepala OR, dan teman-teman khususnya dari ORTN ini sepertinya banyak ini, ya, termasuk Pak Toti dari INUA, ya, Indonesia Nuclear Agency, juga keluarga. Terima kasih dari keluarga Bapak almarhum Siwabessy yang berkenan hadir pada hari ini. And also, of course, the official from China Embassy in Jakarta. And of course, the honorable distinguished professors from INET, Tsing-Hua University, Professor Yuliang Sun and also Dr. Jun Sun. Yeah, so nice to see you again. Yeah, after our last meeting last month. Yeah, when I visited INET and Tsing-Hua University, and I got, greatly impressed with the development and the operation of the fourth generation of nuclear power plant based on the STGR technology, high temperature gas cooled reactor, or according to your presentation, it was called as the STR PM, which is already operational fully. Yeah. So thank you very much. It is a great pleasure for all of us here to have your lectures, and I think it is truly inspiring all of us and motivates us more, in particular our researchers working on the reactor technology, within BRIN, who most of them, I think you already know since many years ago, and some of them are joining us in this auditorium. Yeah. Oh, we have also the director, Dr. Jainal from our Polytechnic for Nuclear Technology. Yeah. So, terima kasih untuk Bapak Ibu semua. Jadi pada hari ini adalah penyelenggaraan Siwabessy Award dan Memorial Lecture yang kedua, yang pertama itu tahun lalu, tetapi sayangnya sama seperti tahun lalu, pada tahun ini kita kembali belum dapat memberikan Siwabessy Award, ya Pak Edi Giri ya, gitu. Saya berharap tahun depan itu sudah ada, ya, gitu. Jadi Pak Saiful dan teman-teman, mungkin Mas Topan, itu ada Pak Saiful, ya. Ada fotonya tadi di situ ya. Masa foto nampang terus ya? Kapan harus nampang di depan HTGR-nya sendiri? Ya Pak Saiful ya, semangat dong. Jadi seperti kita ketahui, ya, Bapak almarhum Siwabessy itu adalah pionir teknologi nuklir di Indonesia, meskipun beliau bukan seorang engineer, ya, nuklir engineer, tetapi lebih tepatnya dokter, ya, tetapi dokter yang mendalami kedokteran nuklir, ya, termasuk radiologi dan sebagainya. Tetapi justru itulah yang membuat pengembangan nuklir di Indonesia itu penuh dengan kedamaian. Jadi nuklir for peace, ya. Peaceful use of nuclear technology, ya. Dan saat ini setelah integrasi ke dalam BRIN, kami telah merestrukturisasi program terkait pengembangan nuklir, ya, baik riset maupun aplikasinya. Dan kami telah menetapkan bahwa Pasar Jumat, kawasan nuklir yang juga namanya Siwabessy, kawasan sains dan teknologi Siwabessy di Pasar Jumat, itu menjadi pusat aplikasi teknologi nuklir untuk industri dan medis, ya, utamanya yang berbasis reaktor. Jadi kita akan menempatkan mulai tahun depan, insya Allah itu sudah akan aktif berbagai iradiator untuk memperpanjang usia pangan dan juga sterilisasi alat-alat kesehatan, ya, produksi alat-alat kesehatan. Dan berikutnya juga adalah infrastruktur yang kita tujukan untuk mendukung teman-teman kita di bawah Mas Heri Yogaswara, ya, carbon dating, untuk menghitung carbon dating, ya, berbagai artefak, manuskrip, dan sebagainya yang juga memakai teknologi nuklir, ya, khususnya akselerator. Di lain sisi, kita akan melakukan revitalisasi, ya, fasilitas nuklir kita yang ada di Serpong, yang disebut sebagai reaktor Siwabessy, untuk tujuan utama produksi isotop ke depannya, sehingga Indonesia tidak akan tergantung lagi pada isotop dari import, dan kalau perlu kita menjadi salah satu eksportir isotop. Ya. Sedangkan di reaktor Kartini yang ada di Babarsari, itu akan kita jadikan sebagai pusat reaktor untuk tujuan pendidikan, ya, bagi teman-teman di bawah Pak Jainal, di Politeknik Teknologi Nuklir Indonesia di Yogyakarta. Selain itu, kami juga banyak mengembangkan, mulai, ya, teman-teman di bawah Pak Rohadi mulai mengembangkan teknologi akselerator, ya, dengan siklotron 13 MeV yang ada di Babarsari, dan tahun depan semoga bisa langsung masuk ke akselerator siklotron 30 MeV, ya. Itu mungkin cita-citanya Pak Edi Giri, ya, sejak lama, ya, gitu. Jadi, tapi Pak Edi Giri nggak ada, bukan karena Pak Edi Giri loh, ya, itu bukan maunya Pak Edi Giri itu, ya, gitu. Tapi maunya teman-temannya Pak Rohadi, ya, gitu. Karena kita harus meningkatkan kemandirian kita dalam penguasaan teknologi, khususnya akselerator, dan juga teknologi reaktor untuk produksi isotop serta teknologi reaktor untuk pembangkit listrik. Ya. Nah, jadi pada kesempatan ini kalau ada teman-teman media, jadi kita selalu bicara kalau nuklir selalu ke PLTN, ke bom nuklir dan sebagainya. Jadi seharusnya memang tidak seperti itu. Ya. Indonesia cepat atau lambat pasti akan membutuhkan PLTN, ya, di tengah pertumbuhan ekonomi, pertumbuhan industri kita yang semakin tinggi, dengan populasi kita yang kemungkinan akan mencapai 300 jutaan, ya, tidak ada cara lain untuk pemenuhan energi secara berkelanjutan, itu memang kita harus memanfaatkan PLTN. Itulah sebenarnya message yang ingin kami sampaikan dengan mengundang Profesor Yu Liang Sun dan Dr. Jun Sun pada kesempatan ini, karena mereka inilah pionir, ya, secara global, ya, tidak hanya di Tiongkok tapi secara global, pengembang PLTN generasi keempat yang sudah operasional, ya, yang kebetulan memakai teknologi HTGR, ya. Ada beberapa teknologi yang lain, tetapi semuanya belum ada yang operasional. Sedangkan HTRPM, ya, yang tadi disampaikan, itu bahkan sudah masuk ke grid jaringan listrik di Tiongkok, ya, secara operasional. Sehingga kita juga belum tahu kita akan memilih yang mana, ya, tetapi BRIN memiliki tanggung jawab untuk melihat, mengkaji, ya, dan juga melakukan riset, berkolaborasi dengan berbagai mitra global, ya, untuk bisa menjawab PLTN apa yang cocok di Indonesia pada saat itu sudah harus dilakukan, ya, itu khususnya kalau yang komersial. Tapi kalau kita bicara PLTN eksperimental, besok pun sebenarnya bisa langsung dimulai, ya, kalau memang sudah diputuskan. Karena khusus PLTN eksperimental itu harus dilakukan di bawah BRIN, ya, tetapi sebagai gantinya itu memang tidak perlu dilakukan proses yang panjang sebagaimana harus dilakukan untuk PLTN komersial. Ya. Nah, upaya kita ya untuk mengembangkan berbagai bukan mengembangkan ya, untuk merealisasikan ya dan memberikan dukungan konkret bagi pembangunan PLTN ke depan di Indonesia, tidak ada cara lain kecuali melalui kerjasama dan kolaborasi internasional. Karena memang kita belum memiliki pengalaman tersebut, ya, belum memiliki ilmunya, belum memiliki pengalamannya, ya. Dan tadi disampaikan mereka saja mengembangkan itu sudah hampir 40 tahun, ya. Jadi dan baru operasional saat ini dengan support yang sedemikian besar. Tentu kita tidak perlu mengulang sampai 40 tahun, tetapi itu jelas tidak bisa dilakukan dalam 5 bahkan juga 7 tahun, ya. Jadi itu harus dilakukan. Basisnya adalah joint development, ya, joint cooperation. Jadi bukan kita beli PLTN HTGR mereka, tidak begitu, ya, karena sebenarnya masih banyak kekurangan juga. Kekurangan bukan dalam konteks keamanan, tapi kekurangan dalam konteks optimalisasinya. Karena kalau yang dari saya kunjungi kemarin, ya, bersama Pak Edi Giri, itu memang masih ada beberapa isu, ya, bagaimana melakukan daur ulang dari bahan bakar yang sudah habis, ya, yang bulat-bulat tadi. Kemudian bagaimana juga bisa melakukan kogenerasi hidrogen misalnya untuk meningkatkan optimalisasi dari PLTN itu, ya, itu juga masih menjadi isu, ya, karena kalau reaktor generasi ketiga itu sudah biasa, ya, ada kogenerasi hidrogen dan sebagainya, sehingga bisa dipakai juga untuk mendukung industri pupuk, urea, ya, dan seterusnya misalnya. Tetapi tantangan-tantangan itulah yang coba kita jawab, ya, bersama-sama dengan mitra global ini, khususnya untuk HTGR, ya, BRIN akan bekerjasama sangat erat dengan Tsing-Hua University dan juga INET, ya, melalui OR tenaga nuklir di bawah Pak Rohadi. Semoga bisa segera mulai tahun depan, ya Pak Rohadi, ya. Itu selain juga tentu kita akan mengirim, ya, dan melakukan kerjasama terkait teknologi yang berbeda, ya, semacam tokamak dan sebagainya, ya, barangkali, ya, ke depan, meskipun mungkin belum sampai pada tataran akan kita implementasikan di Indonesia. Ya, kita masih akan fokus untuk PLTN, apakah itu generasi ketiga, apakah yang skalanya SMR, Small Modular Reactor, atau yang skala penuh, atau yang berbasis generasi keempat seperti HTGR yang baru disampaikan. Ya. Jadi sekali lagi pada kesempatan kali ini saya ingin menyampaikan terima kasih kepada LPDP sebagai pendukung utama, ya, kegiatan kita dan apresiasi talenta nasional yang kita selenggarakan sepanjang tahun, ya, dalam bentuk 6 jenis penghargaan. Ya, ke depan masih akan ada, ini yang terakhir, ya, dari seri 1 tahun ini yang terakhir. Ya, semoga tahun depan kita mulai lagi, ya, 6 penghargaan yang lain, ya, serta juga berbagai pihak yang lain, ya, yang telah membantu proses seleksi, ya, termasuk para juri, dewan juri, ya. Dan sebagai penutup, ya, jadi melalui lecture ini, jadi saya berharap PLTN itu publik akan semakin meningkat awareness-nya terhadap kebutuhan kita akan energi bersih, ya, energi baru terbarukan, di mana salah satu potensi utamanya, ya, yang sudah proven secara teknologi itu adalah PLTN. Ya. Demikian mungkin yang bisa saya sampaikan. Jadi saya berharap ke depan kita akan bisa semakin memperkuat, ya, khususnya untuk teknologi nuklir, itu kerjasama dan kolaborasi dengan mitra di berbagai negara, dengan berbagai mitra pelaku usaha juga, pemain global, ya, karena ini bukan mainan kecil, ya, sehingga Indonesia juga akan bisa mendapatkan manfaat sebesar-besarnya dari teknologi yang memang telah dikembangkan umat manusia secara global. Ya. So again, thank you very much for visiting us, yeah, and delivering a very, very impressive speech, yeah, for all of us. And hopefully we are looking forward to having more cooperation with INET in particular and also with Tsing-Hua University, through Researchers Mobility Scheme managed by Professor Gerrit under BRIN. So, terima kasih untuk semuanya. Saya kembalikan. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Om Santi 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 Om.
Thank you, Mr. Chairman. Acknowledging the success of the Siwabessy Memorial Lecture 2023, we warmly welcome member of BRIN Steering Committee and Deputy Chairman for Human Resources of Science and Technology to extend their congratulatory remarks to the recipient of Siwabessy Memorial Lecture 2023. Commencing with Mrs. Tri Mumpuni, the floor is yours.
Oke, di sini aja Mbak. Oke, Assalamualaikum warahmatullahi wabarakatuh. I think I would really like to thank you, both of you, for having a long journey from your country coming to Indonesia and sharing with us, and it's really giving a profound lecture that Indonesia at the moment really needed. You know, thank you Professor Dr. Juliang Sun and you, Dr. Jung Sun. Well, I know, I just would like 1 or 2 minutes. Electricity is the backbone of economic development. Everybody know that. And due to the climate change, well, luckily I just got back last night from Dubai, the COP28. Every country now trying to reach the net zero emission by 2060. In the context of Indonesia, I understand that if all the potential of renewable energy we have to be gathered, hydro, you name it, wind, biomass, everything, in 2060, we realized that considering with the calculation, Indonesia installed capacity will be 600,000 megawatt. Unluckily that all the potential side, if we want to develop, we only have half of it. So we like or we don't like it, nuclear is one of the alternative. I remember back in 2001, when I was an NGO, I fight against the group of Japanese who came here trying to make a socialization of how important is nuclear. But the technology is not really understood by Indonesian at that time. I'm glad you giving us something that is really mind-blowing, because as our BRIN chairperson told me, nowadays we still in the learning curve of trying to have the best technology, and very important is the safety, what is become the highest priority in Indonesia. So once again, I think I would like to convey my deepest appreciation on behalf of BRIN, and I think what we would like in the future is a very good cooperation, and we would like to learn more from you, and hopefully we can fulfill our energy demand soon in 2060 with more cleaner and green energy. Thank you very much. Terima kasih banyak. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, ma'am. Now I would like to invite Mr. Edi Giri Rahman Putra to share his thought on this momentous occasion. Mr. Edi Giri, please.
Assalamualaikum warahmatullahi wabarakatuh. Very good morning. First, I would like to thank you and appreciate for Professor Lu Liangsun and Dr. Jun Sun for coming here to fulfill our invitation. Because I remember last month we visited Tsing-Hua University, and then I discussed with our chairman, Dr. Handoko. I think this is the best choice for us to invite them to come to here. This is a good time for us because today is the 65 years anniversary of National Indonesian Nuclear Institute, Badan, or Lembaga Tenaga Atom, LTA at the time. So today is the 65 years anniversary. So I think it is a good time to restart again about our vision for the futures. Why? Because last time I asked my colleague, Dr. Topan and Dr. Saiful, this collaboration already established maybe 7-8 years for the joint laboratory from the SHTR. I hope it is not just only joint laboratory, but also for the joint development and joint cooperation more wider and extent than before. So that's why, start from next year, we would like to send our young generation, our young talent, to study, to learn from you how we develop our new generation for our future in the nuclear science and technology, especially for the nuclear energy. So again, thank you very much for the very inspiring lecture for today. So we can learn in detail how we can start from the education, research, development, and industrial application, truly, from this, your experience. So again, I would like to thank you, and I think this is time to open call for our young talents, to join with Pak Rohadi, to this project for the futures, especially. And I hope for the next 20 or 30 years, we can see our own result, our own product, of this science and technology, especially in nuclear power. So again, thank you very much, and congratulations for this very inspiring lecture. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Edi Giri. Ladies and gentlemen, now we are officially at the end of today's event. On behalf of the organizing committee, we extend our heartfelt appreciation to everyone who has contributed to this event. We bid you farewell with immense gratitude and thank you for your participation. Have a great day. Wassalamualaikum warahmatullahi wabarakatuh. Let's enjoy the final performance by the Gita Achitya Choir.
Hujan sore-sore, kilat sambar pohon kenari.
Ladies and gentlemen, please enjoy the buffet located in the middle corner at the back of this room. Thank you.
Salam
Bapak Ibu tamu undangan, kami persilakan untuk menikmati santapan makan siang di bagian belakang ruangan ini. Terima kasih.